Accident, or were you doing that on purpose? Okay. It's freaking me out. But that's how I get all the lectures. As you can see here, I feel like every day these desks get closer. We're like really close together. I have to fix that. Okay. Hello, class. Welcome to Sleepy Monday. We're gonna start on the earthquake section. So last week we talked about plate tectonics, and you have a lab out. So remember to be working on the lab. It should be pretty self-contained. So if you just read through it and kind of go through it, but I'm not gonna lie and say it's easy. So make sure you kind of get started on a little bit earlier this week. You don't have to have it done today or anything, but if you start to work on it slowly through this week, if you have issues, you can bring it into class, and we can I can help you work through some of those instead of just having to work on it on your own. So try to get started on that just so you kind of see if you can work all the way through it by yourself, or if you need a little bit of help on it. So today we're going to start on earthquakes. I do also have an earthquake lab, I believe, very similar to the plate tectonics lab. Maybe not quite as in depth. I think it might be a little bit shorter, but still pretty nice little lab there. So we're going to work through this first. I'll get the homeworks up early this week, so you can have access to those. But this is probably like the most dense part of the semester, because we got a couple chapters in a row where we got labs going on, and homeworks, and then tests for them as well. I think as we get past, I don't think we have a volcano lab. I think after we get past this section, there's a lot less labs. We do have kind of like a weather section that'll be the signature assignment. It's almost like a weather lab in a way, but this could be kind of the last lab you have for the year. I'll look at that and see if that's actually true. I could be lying. I don't know. Too tired to know the difference right now. So we're going to talk about earthquakes. I have a picture here. I believe this is the presidential mansion in Haiti. And they had a Haiti earthquake, which I believe was 2010. That was a pretty bad earthquake. A lot of international aid was needed. I think mainly because a lot of their buildings were not built to withstand any kind of major or even moderate earthquake. They had a lot of damage. Here in the United States, we've done okay. The good part is the vast majority of the United States is not under threat of an earthquake, so we don't have to worry about it too much. That being said, there's still a lot of room to grow, and ways to do things a little bit better to kind of protect ourselves from earthquakes. A place you might want to model yourself after would be like Japan, who has very strict building codes and retrofitting codes, and is trying to make their city as earthquake proof as reasonably possible, because they are constantly under threat of an earthquake, and it's kind of like the entire country. I don't think there's any part of Japan that's like, no, we don't have to worry about earthquakes here. Like in Texas, we don't have to worry about earthquakes. There might be small ones from time to time, but they're not going to do anything more than slightly damage your foundation, possibly, or maybe even cause a couple cracks in your walls. But I don't think a house has been destroyed in Texas due to earthquakes in a very long time. Tornadoes, different story. So this is just a picture of some damage from a recent Haiti earthquake. And next semester, as we go through the different types of human-earth interactions, we'll spend a little time talking about earthquakes and the damage caused, and how we kind of work through that. So what is an earthquake? Where does it come from? What are some terms we use to describe it? A fault is where we're starting off. So we talked about plate tectonics, and faults are not necessarily going to be always plate tectonic interactions. Sometimes they are, and a lot of times they are, but not. You don't have to be right on the edge of two different plates to have major earthquakes. It does help, but it's not mandatory. So their example here of a fault is just two large pieces of rock or sometimes crust. They're going to call them blocks, slipping past one another. And when that slip happens, you're usually releasing strain. And they'll get to this in another slide. It's all about strain. And so I'm going to use a stick, and I think they will have an image later that kind of uses a stick as an example. The buildup, and everybody can see this online, the buildup of strain bending the stick is the precursor to the earthquake. So in order to have an earthquake, you have to have strain. You have to have some sort of energy built up inside the rocks that is released when they slip. If they're constantly just slipping and you never get that buildup, you might have small earthquakes, but there's not going to be any large earthquakes. And so it depends on the type of fault and how things happen. But if they get locked, which most faults are, once they get locked, then you build up your strain until the point where something gets overcome by that strain and it has a slip, and then all of your energy is released. When that energy gets released, what is the actual earthquake? That is seismic waves moving out from the center of the earthquake, which we call the focus, to where, which is basically where the slip begins. We have two different terms for this. The focus is where the actual earthquake happens. The hypocenter, no, wait. No. The hypocenter is another word for focus. I was thinking epicenter. The epicenter is where it happens on the map. So usually when you see an earthquake on the news, they talk about the epicenter. That shows you the general location of the earthquake. It doesn't show you how deep it was. The epicenter never includes depth. And so you can have shallow earthquakes, you can have deep earthquakes. The epicenter is just a map point that doesn't include depth. The focus or the hypocenter is the actual point of slippage as far as we can tell from the seismic waves. Now, we'll get to seismic waves in a second. So here's an image to kind of help illustrate that. Here's your focus or your hypocenter down below the surface where the earthquake actually happened. If you trace it straight up to the map, you get an epicenter, which is what they'll show you on the news. And all of your waves kind of radiate out from that. In general, we don't live underground. We only live on the surface. And so for humans, as far as damage is concerned, the epicenter is going to be the most important one. That's where you're going to have the most shaking and the most damage, more than likely, or at least the area immediately around the epicenter. As you get further and further out, it kind of gets kind of dampened and it doesn't affect the surface as much. Let's see. Weak earthquakes can be generated by several different things: volcanoes, landslides, meteorite impacts. Those aren't going to be your super strong earthquakes unless maybe it's an asteroid kind of impact. But in general, those are usually going to be weak. Destructive earthquakes, like I said, generally tend to line up with plate tectonics. You have to have a large amount of motion and a large amount of strain built up for your really big earthquakes to occur. The really big ones don't generally occur inside a continent, but on the continental edges. So you need that friction, you need that strain to happen. And what they call this as an earthquake happens is elastic rebound. And it's the idea that you can build up the strain, which I think they have stress here, but strain is more accurate. You can build up the strain. When this stick snaps, if I were to just keep bending it until it snapped, would the left and right piece stay curved like this? No, they go back to straight afterwards. And that's actually what happens in an earthquake. And that's what they're talking about with this elastic rebound. Elastic meaning that it can flex and move and return back to its original position. And rebound meaning that it's going from one place back to its original position. So elastic rebound is going to be your stick after the break, kind of returning straight to a flat area. And we can see that happening with the ground as well. So here's how it happens. This is going to be a transform fault, similar to the San Andreas fault in California, which we'll see in a second on a different slide. Here's your predeformed state. So you can see all the rivers go straight through the fault line. Nothing really seems deformed, and their example here, the stick is straight. You start to build up your stress and strain. The stick is curving. The rocks are actually being pushed and curved. Notice that on the surface, unless you're using like GPS equipment or have some sort of idea of what's going on, nothing's really disturbed at the surface here. The rivers are all still flowing straight across the fault line. Other than, maybe if your house is here and you're used to looking at the mountains, you wouldn't really notice that shift has taken place because there's no real disturbance on the surface, just some lateral positioning movements. Then all of a sudden, all of this stress and strain that's built up in our stick here and in the ground is released. It overcomes whatever's holding it back. In the stick example, it would be the bonds between the wood. And in the earth example, it would be the catch on the fault, the friction on the fault, keeping it from moving. All of a sudden, it gets overcome by the force of strain and stress, and your earthquake happens. The movement happens very suddenly. In their example here, the stick breaks, and all of your strain and stress is relieved. Notice that the curve is gone afterwards. You can see it immediately. The curve is gone. You have two straight blocks here now. And at the end, you've had this movement happen. So down here at the bottom, the streams which were going straight across the fault line are now cut, and the streams actually have to follow along the fault line. In the stick example, your stick is now broke. And all your energy that was built up as your stress and strain has been released. So here's an example of the San Andreas fault line. They have two little pictures to kind of show you from the most recent major earthquake. That's not the most recent major earthquake. They had one in the 80s where like double-decker highways collapsed. I think that might have been in Oakland. And so not the most recent, but a relevant major earthquake in on the San Andreas Fault. So this was in 1906, San Francisco. You can see this person's fence has been offset. And notice you don't see like a huge crack here kind of showing you what caused the movement of the fence. They just had an earthquake, and now my fence, which was a normal fence, 5 minutes ago, is no longer a normal fence. It's got a huge gap in it because the left half moved this way, the right half moved that way, and now my dog can get out of the yard, which isn't great. You can see the same thing. This is an orange orchard. Is that right? Orange grove. There you go. They call it a grove, not an orchard. My bad. So this is an orange grove, and you can see straight lines all the way down, all the way down, all the way down, and then all of a sudden, not a straight line anymore. It actually curves over to the left, and you can see right here that it's taken this like sharp curve here to the left. That shows you the offset, and you can see the fault has kind of run right up this direction diagonally through all the trees and giving you that offset there. And so there's no major crack. It's not like the movies where they get like a big gorge opens up and someone falls in it. Although that can happen. There's some interesting pictures from some Alaskan earthquakes that have some pretty big cracks. You've just had that offset, that removal of strain as the stick breaks in a way, and your fault is released, and it lets all that movement happen. So here's an actual illustration of the San Andreas Fault moving along kind of the coastline of California. And I'll point out that, again, California is not going to like fall off into the ocean like some of us want it to happen. Sorry, California. It'd be, I don't know. It'd be movie worthy to say the least. But it's not going to fall off into the ocean and like the waves come and take it and we're ridden of Los Angeles area and their terrible traffic. But actually, it's a strike slip fault. And so it's just going to move relative to one another. And you can see Los Angeles is headed up this way. This plate's kind of headed up that way, and they're just going to continue to move. So actually, if you wait long enough, which won't be your lifetime or anything, but if you get in a time machine and go to the future, San Francisco and Los Angeles would just continue to get closer and closer and closer to each other, and eventually will just be one metropolis nightmare of traffic that no one can escape, and just you live in your car. Everyone will own RVs because they never get off the highway. By the time you get home from work, it's time to go back to work again because the traffic will just be terrible. Or maybe we'll have flying cars by then. Or personally, I'd like to see like some the Jetsons tubes where you just step. Oh, they had them in Futurama too. Where you just step in the tube and like a bank tube, it just sucks you up and like takes you where you need to go. I think that'd be pretty nice. So let's see. They have a couple of these sections of the faults kind of identified. They point out that here in the green, there's actually no locking of the fault. It's just what they call a creeping fault. So it constantly just slides past each other. And there's not any really big stress or strain built up in this area. And so while it may suffer the effects of either one of these areas having an earthquake, right here in the middle is probably not where it's going to start. It just has, I guess, a relatively smooth fault line, and you don't get any fault lock there, and so they're constantly moving past each other, not building up strain. But you have had a couple major earthquakes here. 1857, one has happened right here. 1906, one has happened right here. I don't know where Oakland is compared to this, but I know that there was one, like a pretty big one in the around 1980 or in the 1980s in Oakland. Look that up for me. California earthquake in the 80s, maybe? I don't know how to look it up.
I think I saw a documentary about that. And like the sports, I think there's like a
yeah, they were like playing a baseball game or something when it happened. And they have like the double-decker highways where you can drive on the top or the bottom, and they like collapsed on top of each other. What year was it? Can you see? 1980. See, I was right. And was it like the Oakland area or Humboldt County? All right, that's close enough. I don't know where that is either, but now we know. Humboldt County, 1980. So they do point out here 1906. I don't know how close that is to San Francisco, but they say that in this 1906 earthquake, it likely released the strain that had been building up during the previous 200 years or so. Well, we're over 100 years past that, and so if the strain hasn't been released since then, we're kind of well on our way to another large earthquake in that area. You never know when it's going to happen, but likely it will happen. It's not a if, it's a when kind of thing. So they talk about what is an earthquake. If you can have them at convergent plate boundaries, you can have them at transform plate boundaries. You do get earthquakes at divergent plate boundaries, just not very big earthquakes. You can't have as much stress built up if everything's pulling apart. They have lots and lots of small earthquakes, but again, most divergent plate boundaries are underneath the ocean in the middle of an ocean basin, and so humans are not affected by them at all. It's just a kind of an interesting thing that happens. But your convergent plate boundaries do get some of the biggest ones. You have that compressional force. They build mountains. They have faulting associated with it and large earthquakes, and mainly because of the subduction of the oceanic plate underneath. So if you think about the setup that Japan has, it's pushing that plate underneath. The continental plate kind of gets stuck on it as it goes down. You get that fault lock. And then all of a sudden the strain overcomes it, and your continental plate kind of rebounds a little bit, which causes your major earthquake. So the subducting plates form what they call a megathrust fault, which gets your most powerful earthquakes vis-a-vis Japan and how they have really, really strong earthquakes. So like I said, the mechanism that generates large earthquakes is stress. Stress built up in that locked fault line. That stress causes strain. So let me just give you an example of these two terms. Stress, like engineering-wise, is going to be the force applied to this stick. I'm giving it stress. I'm stressing it to make it bend. The strain, which I mentioned kind of as flip sides of the coin, strain is going to be the actual bending itself. The effects of the stress on the rock or on the stick. That's how we see whether the rocks are being stressed or not is if they show strain. Let's see. Seismic waves propagate out from the hypocenter and actually cause the earthquake when all the stress is relieved. So, what are seismic waves? Seismic waves are essentially just energy being released, but I want you to think of them almost as sound waves. And we listen to them in the same way as sound waves. So in the same way, my voice is coming to you through the air. Does everybody know how voices work? So you have vocal cords inside. You put energy into your vocal cords, and they make a vibration. That vibration hits the airwaves inside your throat, and literally causes like a shock wave to go out. As my vocal cords hit little air molecules, they hit other air molecules and hit other air molecules, and it just creates this like wave of energy passing from molecule to molecule all the way until it reaches the air molecules inside your ear. Those hit your eardrum, which is very sensitive. If you've ever like poked a Q-tip too far into your ear and touched your eardrum, it's very loud and painful. It's not, you're usually like, whoa, I'm not going to do that again. So that's kind of how it works. And that's why, have you heard the like sound doesn't travel in space? In like space horror movies, they put it this way, in space, no one can hear you scream. Which is true, because there's no air molecules. There's nothing to transfer that energy of motion from someone's mouth to your ears. And so you can't hear things in space. Now, if you're in a spacesuit and you have like a radio inside your spacesuit, you can hear things. They can talk to each other inside their spacesuits. But if you were just to go out into space with no spacesuit, they can't hear you. Or if you didn't have a radio and you just tried to yell from one person to another, they're not going to be able to hear you. So that's just how sound works. And seismic waves for earthquakes kind of work the same. You have this energy released by the stress built up in the fault line. All of a sudden it's released and makes this motion, and that motion travels from molecule to molecule inside the earth, each molecule hitting the next attached to it because it's a solid. They're all tightly packed. And so that motion just travels outward in the same way sound waves travel outward in pretty much every direction until they get far enough away where you can't hear me. So, if you're sitting in the back of the room, Tanner, I wouldn't be so loud because I'm sure I'm just constantly yelling right at you. And, if you were on the other side of the building, you wouldn't be able to hear me at all. The sound waves are still there, I guess. Maybe they don't make it all the way there. Maybe if you had a good enough microphone and everything was silent, you could still hear Mr. Bailey droning on and on about earthquakes. But after a certain amount of time, after every molecule hits another molecule, little bits of energy are lost. And over time, it's not even enough for you to feel it. In the same way, we'll get to that in a second. The earthquake waves still make it here from California when California has an earthquake. We just can't feel it. It doesn't shake our houses. It doesn't shake the ground. It's not a big deal. So we're going to talk a little bit about waves, about seismology, about seismic waves, seismometers, which are what are used to read seismic waves, and the graphs that they put out, seismograms, so we can look and see what the waves actually look like. But it's all about ground motion. It's all about how the ground is moving, how that energy wave, that physical motion energy wave is transmitted from one molecule to the next all the way basically around the earth. So how do we read that? We get a seismograph. No, wait. What did they call it? Seismograph is the graph. Seismometer, sorry. A seismometer, like a thermometer, measures heat. A seismometer measures seismic waves. And so this one is one of the first ones that we had. Actually, one of the first ones ever that we had was a simple like pendulum. So they had a little rack kind of hung up, and then they put a weight with a point on it, suspended over like a sandbox. And when an earthquake would happen, the sand, which was attached to the ground, would shake and move, and the pendulum, which was still kind of attached, but it was allowed to swing, would generally stay in the same place. And as your sand shook and moved, your pendulum would draw like lines in the sand. And that's how they kind of understood a little bit about earthquakes at the very beginning. It's still very rudimentary. They didn't understand any of the science. The Chinese, obviously, talking about any kind of technology, the Chinese usually got to it first. They had these complicated, kind of like a vase with either dragons or frogs all around every side. And the dragons or frogs would have little balls like stuck in their mouth. And when the earthquake happened and it shook, especially if it was a single direction earthquake that maybe just shook from left to right relative to us, only the dragons or the frogs on the left and the right of the vase would have the balls fall out of their mouth into the tray below. The dragons on the front and back didn't get that shaking that would cause the ball to actually come out. And so this vase could actually like show you what direction the earthquake happened in. This is a little bit like slightly more technologically advanced, but not super, not like what we have today. So what you have, just like your pendulum hanging down into the sand, you have a pivot point here and an arm, which is kind of hanging from a wire. This basically kind of insulates your arm from the movement of the earthquake. So the idea is when you have an earthquake, the base and the paper and everything except for the arm moves with the earthquake. In general, the arm's going to move a little bit, especially if it's a strong earthquake. But in general, the arm's going to stay exactly where it is. And so as the paper shakes beneath the arm, you have a little pencil or a pen, which is drawing on the paper, and it draws like your earthquake. Now, to keep all the lines from being right on top of each other and it like not legible, you have the paper on a drum that actually spins around. And so you're constantly drawing on a fresh part of the paper, which gives you a nice seismograph. So this is an actual picture of the drawing that they have here. You can see the shaking happening. And actually, I bought one of these using science department funds. So we actually have one of these, and we can set it up later this week if you want. It takes a little while, and it's not, I don't know. Obviously, we don't have earthquakes around here, so we're not going to pick up anything great. It's not super duper sensitive, but I believe in previous years, if I've got it set up right and I have it kind of tuned down where it's not just picking up everything. And I think you have to have like a box over it or have it hidden somewhere because when the air turns on, the air blows it and makes it pick up a lot of stuff. It's very sensitive, but not like professionally sensitive or anything. But I believe when we set it up and we have everything set up right, we can stand next to it and like jump up and down and cause an earthquake. And it reads out on the computer. So basically what happens here, you have your arm. It's got like a little pivot point here, which is literally almost like a razor blade. It's pretty sharp. It's not like super duper sharp, but it'll cut you. Stuck in just like a little groove here on the side. Stick it in the groove. You've got a spring kind of holding up this magnet at the end. They even have a tub. I took it out because it had just been there for years and it's kind of crusting up. But they have a tub, and you can put like an oil in here. I think I used maybe mineral oil to just kind of dampen it a little bit to keep it from just constantly bouncing forever. And so you can use different liquids in there to kind of keep it from moving unnaturally and only move when it's supposed to. But essentially how this works is when you have an earthquake, the ground moves. So like the table will move. This is still moving, but the little coil of wire underneath moves in between the magnet ends, which creates an electric current. It's kind of the same way. You probably haven't looked at it, but have you ever looked inside like your ceiling fan, like through the little holes in it? If you look in there, go home and look inside your ceiling fans. You can see like a coil of wire inside your ceiling fan. And what actually happens is you have a coil of wire inside the ceiling fan, and at each of the fan blades where they attach to the ceiling fan, there's a magnet. And so this actually works the opposite way. At your house, you turn on the light switch, it passes electricity through that coil of wire, which creates a magnetic field, which pushes the magnets at the end of the blades, which causes the blades to turn and to actually make wind. We're doing the opposite here. Instead of having electricity push our magnets, we're having the energy from an earthquake push the coil, which moves the magnet around the coil, which creates electricity. So it kind of does it backwards. That electricity goes through this wire, which we plug in through some other cables to the computer. We have a program up that reads that signal, and it can actually tell you how much movement you have on your seismometer here, which can tell you how much energy you have in your earthquake, which is actually pretty fun to do. So maybe I will set that up. Yeah, nice. What time is it? Can I stop talking now? 8:20. We got about 7 minutes. I think that might be where I'm going to end. Let's see what the next slide says. Let me just introduce the waves real quick. So we have two different main categories of waves, which we won't talk about a lot. The names themselves kind of lead you to know exactly what they are. We have surface waves, which travel along the surface, and we have body waves, which travel inside the earth, in the body of the earth, if you will. So they travel through the Earth's interior, where the surface waves just travel right on the surface and don't really translate down into the interior. So here's an example. Your body waves will come down. They curve due to refraction in the same way that when you see something at the bottom of your swimming pool, it doesn't really look like exactly where it's at. The waves have been kind of bent. So you have that as you're traveling through the Earth's surface. So the waves do kind of curve around, but these are all body waves. And then you will have surface waves that travel right along the surface here, outward from the epicenter. And we'll talk about how you read these on a seismograph later during the lab. But there are three different types of waves specifically that we look at. We have P waves, S waves, and then, there they are, surface waves. Those are your three different types of waves: P waves, S waves, surface waves. The surface waves are obviously, wait, is that right? Yeah, P waves, S waves, and surface waves. Yep. All right. Just threw me off for a second because they talked about surface waves and body waves, but we kept that name going. All right. Your P waves and S waves, a good way to remember it is primary and secondary. Know that somewhere down the line, the P and the S don't actually stand for primary and secondary. This comes back from, like, I believe, the French language. And it's two different words, not primary, not secondary. But those do help out. And we'll see why later. But those are two different types of waves for your body waves. Oh, if I go back. So your body waves are going to be P waves and S waves. Your surface waves, we literally just call surface waves. There's a lot of different ones. We're not going to learn about each individual one, but we'll just talk about surface waves as a whole. So that's a nice introduction. We got 12 slides in, not too bad. I think we can finish this PowerPoint this week and talk about the lab a little bit. So for those of y'all still at home, I'm just going to say it. Maybe consider coming back to school. We all miss you, and we wish you were in class. And it's probably a lot easier to learn when you're in class. I don't know. Although sometimes it makes you very sleepy. So that happens. So everybody have a nice day. If you have questions, please email me. And I hope you watch the video. Have a good one.